All right, so let's start. It's the 4:15. Okay, let's start. So let's quickly go over the previous lecture. We have so the first one. Let's see, what is this? Okay, the r is equal to 3. Suppose the measure of the arc is 120 degrees. That means the angle of the angle of the AOB is 120, right? So one of them, if I just use the OH to be perpendicular to AB, then that is actually angle bisector. So each of the angle is 60 degree, and therefore we get the 30, 60, and 90 a right triangle, right? And then we can do the rest of them. Okay. And this is a warming up. Where why do we do this? Because this is for a measure the estimate pi, right? So this is a very nice where by itself it's a very nice problem, right? You have the rectangle, and then you have a base of CD. You make a triangle, and this area of the triangle is actually one half of the area of the rectangle, right? So yeah, so it's just yeah, so that's this. Okay, and circumference of a circle. Okay, and now, so here's how do you define the pi, where pi is defined to be a circumference of a circle divided by the diameter, or divided by 2r, right? We can get that. So that's the definition for pi. And the question is, how do I estimate the pi, right? So some of the idea is that, let's see, the circumference of the regular polygon of six sides is less than or equal to circumference of the circle, right? And then it's less than or equal to circumference of the regular polygon, which is outside of that circle, right? So you can work on that one, right? So that's one kind of idea. You can do that. But that one give you pi between 3 and 3.464. Right? Well, that's just because the number size is too small, right? It's only 6 for convenience. We can do that. So if you want to get some good estimate, you can imagine 6 is not enough, right? 6 sides, regular polygon is not enough. You may try to do 12, and then you do the 24, and then you do the 46, 24, right? 48 and 96, and so on and so forth, right? That's one idea for that. Okay, we're going to talk about that today later. And yeah, the other day we talked about a different idea. We are working on the area, right? Not just for the circumference. We are working for the area. So here is a different idea for this. The area of the circle is bigger than an. What's the an? An is the area of the regular polygon of n sides, right? So you have the regular polygon. It's inscribed to to the circle, right? Certainly, the area of circle is bigger than AN. But I want a upper bound. How could I get upper bound? And that's very smart. So this is actually from the warming up exercise, right? That's from the warming up exercise. So for each of this, right, I want to make a rectangle, the red part, right, the rectangle. So the rectangle here, together with the circle, all together can cover the entire circle, right? Okay. So that gives it the upper bound for the area of the circle. But how do I estimate that? How do I estimate that? Well, so you can actually do in the following way. Basically, what's the green area? The green area is A of 2n minus A of n. Why? Well, think of that for a couple of seconds, right? So we have let's see, right? So this is the green area, right? The green area, right? We get that, but the green area was obtained between the regular polygon of n sides and the regular polygon of two n sides, right? So that's why it's a difference of this, right? The difference of two areas is equal to that's the green area, but the green area is actually same as the red area, and that's the same. That's just our warming up exercise here, right? The two of them are the same. Okay, so that's because of that, and therefore, so that's the same as the red area, and therefore the area of the unit circle, right? The area of the unit circle is smaller than this. Okay, let's see why. Okay, let's see why the area of unit circle is smaller than that. Well, certainly it's smaller than 2n and A of 2n, right? That's the area of the regular polygon of 2n, and then add the red area. So that covers the entire circle, right? And the red area is just the same as this one. So that coming up together, we can have this. So that's why we have this. This is very smart, right? So based on this, and then someone, over 2,000 years ago, right, and finished almost 2,000 years ago, right, finish the estimate. Okay, we don't go to the detail, but it's just the good idea, right? That's a good idea. Okay, anyway, so that's from last time. Are there any questions? Any question? Okay, and so today I'm going to go to let's see. We still have actually one more idea for estimate the pi, but depending on how much time do I have, so the estimate could be long, could be short. So I just decide to finish the rest of the part of lecture first, and depending on how much time I have, and I come back to do one more estimate. Okay, so let's see. Let's do this. So today. Let's go over one homework problem. Okay, let's go over one homework problem. Let's see. Okay. All right. So I'm going to do the review homework. So homework number 1. Okay. Let's do the last question. Seems to be a little bit hard. Number 10. Let's do number 10. Okay. So everyone have that problem in hand. Question number 10. Okay, homework 1. Okay. So let's see. Let me draw the picture. So you got the first of all, I have a quarter of a circle with radius 8. So this is a right angle, and I get so this is a quarter of a circle, right? And then you are going to draw 2 semicircles. So suppose this is your the base here is your diameter. So I'm going to get maybe somewhere here. So I'm going to get something like that, right? This is a semicircle, and I can get another semicircle like this, like that, right? So and so my question here is that I want to figure out the area of shaded region. So let me call that this area is X, this area is Y. So basically, I want to figure out the X plus Y. You know what I mean here? X just means the area of that part, right? Y means the area of the middle part here. So I want to figure out the area of X plus Y. Okay, it's an interesting problem. Let's give everyone 30 seconds. Let's think of that. Okay, let's think of that. It's tricky, a little bit tricky. So if you know your answer already, please send me a chat. Yeah, someone got the answer already. Right, so how to get that? Excellent. We get a couple of people get the answer already. So you get your answer should be 16 pi minus 32. Or if you write a decimal, it's 18.24. Okay, right, very good. So let's see how we can do this. Okay. Well, so first of all, I want to show that the x and the y are actually the same. Okay, y, x, and y are the same. So first, I want to see the, let's see, if I want the x minus y, so x minus y, what is this? Okay, well, if I want x minus y, what can I get here? So I can do the following. I can first use the a quarter, the quarter of a circle, right? So that's 8 and 8. And I can minus the semicircle, minus this semicircle. This is 8 here, and minus another semicircle. So I can do like this. Can you see that? So it's not 8 times. It's I just 8 is just mean the names of the sign. Can you see that? So if I use the addition subtraction using this way, this actually give me the x minus y. Why x is there? X is simple because x was not covered by either of the semicircle. So x is outside, is left out. Why y should be negative? Because y was take out twice, right? Y was in the in both semicircles, so it was there twice. Okay, and if you work on this, the first one is 1/4 times pi r square. The second one and third one, I put them together, it's just a pi r square, right? Pi r, but r is actually 4, pi r square is 4, and this is actually equal to 0, right? So x and y are the same, all right? So this implies that the size of x and y are the same. So I just need to count one of this, right? I just need to count one of this, but let's try to count y, because to count y, I can do it by using the previous problem, right? The previous problem. So this actually go back to the previous problem. So that is the, well, let me just do that here. All right, so I'm going to use the hairpin line here, hairpin line here. I want to figure out the y. Right, then this part is a 4, and this part is a 4 by the symmetry here, right? So basically y is inside a square of length 4, right? And then according to what we did in class last time, you will have you will have a quarter of the circle with radius 4. So this is a quarter of the circle, right? Pi r square, and plus another quarter of that circle with a radius of 4 and minus the 4 square. So this is actually the y, right? This is actually the y. Okay, so let's see, what is this? So I get the 1/2 times pi r square. Square is 16, right? And then minus the 16, so I get 8 pi minus 16, right? So that's just for x or for y. And then you double that, so that final answer will be the answer of x plus y, just twice of that is a 16 pi minus 30 minus 32. Okay, so that's a homework problem. Very good. Okay, so I finished my homework, and other homeworks seem to be okay, right? The rest of them should be fine. Okay. Anyway, so let me move on. Okay, as I say that I'm going to finish my today's lecture first, and then I will go back to estimate pi again. Okay, so let's see. Well, so today we are going to basically, I'm going to introduce a theorem. It's called inscribed angle theorem. And now we are really talking about the circle. Okay. So let's see. First of all, we have the in the first lecture we know the measure of the arc, right? So just review that the measure of our arc, right? What does that mean? The measure of the arc is just the so suppose I have a circle here, right? I have a circle here. Assume that this is A and this is B, right? And this is center, right? The measure of the arc is defined to be, so AB is the measure of the arc is defined to be the angle of the AOB, right? The measure of the arc is the same as the angle of AOC, right? It's a central angle cut in that way, right? So that's our definition, okay? And we need that, so today. Okay, oh, wait a second. I still have the two more examples, and then we go to the inscribe the angle. So sorry about that. Right, so let's see. All right, so I'm going to give you two more examples for today. The sum. Okay, so the next one is suppose there's a circle here, and then I'm going to get let's see. So suppose we have a sector, so that's the A, O, and B, right? And then suppose the central angle is theta, right? And I connect this, so it's a triangle of the ABC. And then I'm going to have that shaded region. So, for many problems, we are going to find that shaded region. So this is called the circular segment. It's called the circular segment. Circular segment. All right, and some of the problem will be in geometry where we find the area of that the circular segment. So what's the area for the circular segment? Well, that's easy. So first of all, you can say I'm going to use the area of that segment, right, to subtract the area of that that triangle, right? My picture was not very precise, but it's you know what I mean here. So let's redraw that picture a little bit. Okay, so supposed to be like that, right? And go down a little bit, right? So that is that is like that, right? So let's see, what's the area of the sector? Where the area of the whole thing is pi r square, right? That's the whole thing, right? And then we take a portion. The portion will be theta divided by 360, right? Because the whole thing is 360 degrees, and then your angle, let's say in terms of the degree measure, let's say it's a theta. So that is the area of the sector, and then minus the area of the triangle where we don't know the sine function yet, but anyway, so I'm not going to do that. Anyway, so where if for those of for some people who know Pre-calculus know the sine function, we actually have a formula. So, but if you didn't know that, that's okay, not a big deal. So I can write that to be 1/2 times the r squared times the sine of theta. Don't worry about that. If you don't know the sine function, if you don't know the area of that triangle in this way, not a big deal. I just write here. Okay. Anyway, so let's see. Next question. So let me give you example. Okay, let me give example. So suppose we have a circle here, right? And suppose let's say you got the A is here, and you got the B here, right? And then I can connect that, connect this, all right, over here. And let's assume that the radius of the circle is equal to 1. And I give you the AB is root of 2, okay? And I want to figure out the following, okay? So let's see. We're not the circular segment. The circular segment is easy to do. We can have the formula above. But now I want to do the following, okay? Let me go from the AB. So I'm going to draw a semicircle with the AB as the diameter. So I use AB as the diameter. I want to draw a semicircle. Okay, so let's draw a semicircle like that. Right, semicircle like that. And then the shaded region is here. I want to figure out the area of that shaded region. So find the area of the shaded region. Okay, so let me give everyone a minute. Let's try this. So let's see. What can we do here? All right. So let's say, first of all, I know that let's try to figure out the triangle, right? So this is 1, and this is root of 2. And you know that this is a right triangle, right? So this is a right triangle. So you got that. First of all, I got a right triangle here. Okay. And then how could I get the shaded region? You're going to use some inclusion exclusion. Okay, you're going to use some inclusion exclusion. So let's see, what can I do here? All right. All right, let's see. So first of all, I'm going to use the a semicircle. So I got a semicircle, right? So this is the AB, right? I use a semicircle here. And I'm going to add the triangle here. So this is the AB, and this is the O here, right? So I'm going to add the two guys. So I got the whole thing. And now I'm going to subtract the sector. I'm going to subtract the sector O, A, B. And that will be my shaded region. Right? Does it make sense? Right? So give everyone 10 seconds. Right? That's a strategy. Right? You first add the semicircle and with the triangle. Right? And then you subtract the sector. So that's your area. That strange area. Okay. And so let's do it. So let's see, let's work it. Okay. The first one here, it's a pi, it's a 1/2 pi r square. R is just a root 2 over 2, take a square, right? It's a semicircle, that's why 1/2 and a pi r square. R is 1/2 times square root of 2. Okay. All right, what's the second one here? The second one here, it's just 1, and then you got the right triangle. So it's just a half times 1, take a square. Okay, what's the third one here? Third one, that's the right triangle here. So it's a quarter of pi r square, right? A quarter of the pi r square. Okay, so what is this guy here? This guy is just a half times pi, and the square of the root 2 over 2, that's another 1/2. And the good news is that this is a half here, right? Okay. And so the other one here is a minus 1 over 4 times the pi. The good news that is that the 1 over 4 pi cancel with a 1 over 4 pi. So that's actually 1 over 2. Okay. The amazing thing is that the area of the shaded region, okay, this one, the black shaded region, is actually the same as if I use the a different color here. Let's say, let me use a different one. The green one. The green one shaded region and the black shaded region, they are the same. Okay, that's amazing. They are the same. So you're changing the area of the right triangle to the area of the very strange shape, right? Look like a moon, right? And the two areas are actually the same. That's amazing. Okay, they are the same. Okay, can you see that? They are the same. Okay, so anyway, so just make you know this. Okay. Any questions so far? Any question? Okay, just give everyone 1 more minute. I think that's a very nice problem. All right, so someone just tell me that in the Google form in the homework one, question number 1G, the answer should be 108. Okay, I'm gonna make a change. So my original number was typed wrong, so that's not right. So it should be correct answer should be 108. Our actually I just changed that. Okay, just change that. Okay. All right. So let's see. Today we're going to cover the inscribed angle. It's called the inscribed angle theorem. Okay. So let's see what is this. So it's an inscribed angle theorem. Uh, First of all, I'm going to give the definition. What's called the inscribed angle? So suppose you get oops. Let's see. All right. Suppose you have a circle here, right? And then assume that this is the P, and this is Q and R, right? So Q is here and R is here, and then I can get an angle here, right? And so I can say that, I can say that the angle PQR is inscribed in the arc PR. Okay, so you see that. So you have an arc here, PR, right? And the Q can be anything, can be anywhere, but not on the arc of the PR, but just outside of that. So Q can be here, right? And then you have a PQR, and that's called the inscribed angle. Okay, that's called the inscribed angle. So it's so the angle is inscribed in the arc of the PR. Okay, and you can choose Q to be anywhere you want, like as long as it's not on the arc. So Q can be here. That's also, let me use the Q prime to not confuse you. So you get another inscribed angle here, right? So this one is the inscribed angle, and this one is the inscribed angle. Anyway, so you have lots of this, right? You could have the other Q here, and that's also called the inscribed angle, right? Everything's okay? You get an arc, and you get an inscribed angle. Now, today, I'm going to, so this is called the inscribed angle of in inscribed angle of PR. All right. So this angle is called the inscribed angle of PR. And then, so and then people just say, well, wait a second, you have three different angles here. How can you call all of them the inscribed angle of PR? In other words, are those three inscribed angles the same or different? Right? If they have the same measure, then you can say that that's well defined. But in the case that if one angle, I just make a number, all right? If one angle is 35, the other one is 36, the other one is 37, then that's a bad definition. Does it make sense? Right? I cannot call all of them to be the inscribed angle of PR. So in order to finish it there, I have to make sure that all of those inscribed angles are the same. The same means they have to have the same measure. In other words, if one measure is 35 degrees, any other inscribed angles should have the exact same measure. So that means my picture here, 35, 36, 37, that does not happen. Okay. So let me put it back here. That does not happen. Okay, right. So how do I know that? I need to prove this, right? So this is called the inscribed the inscribed angle theorem. Okay, so what is the theorem? Okay, let's see this. The theorem says that basically it says that where the angle of the PQR is 1/2 of the measure of the PR. Okay, so that's my theorem. Okay, so let's try to understand what does that mean. Well, I just proved that for one angle, one inscribed angle. Because if this is true for one inscribed angle, it is true for every inscribed angle, right? And as a corollary, it just says that all of the inscribed angles, right? If they inscribed of this inscribed in the same arc, then all of the inscribed angles they have the same measure. The measure is just 1/2 of the measure of the arc. Okay, all right. So let's see. So let me just try to prove this, but I want to give everyone 1 minute. Okay, let's see. Can you prove by yourself? Let's see. Let's try that. Then. All right. So let me just draw the picture again. All right. So let's see. If I have this, let me just put the one of this here. So P is here, and R is here. And I got a Q is here, right? So I want to show that this angle is actually 1/2 of the measure of the arc. Okay, so think of that. Okay, but how do you get the measure of the arc? The measure of the arc means what? The measure of the arc means the measure of the central angle to the P and R. Okay, so in other words, the measure of the arc, I have to look at that from the center of that circle. All right, so in other words, this is just 1/2 of the P, O, and R. Does it make sense? So my question is that why the angle Q is 1/2 of the angle POR. Okay, give everyone 1 minute. Okay, so let's see how to prove this. Okay, I'm gonna go in this way. I'm gonna connect the OQ. Okay, and make a little bit extension here. All right, make a little bit extension here. So here I want to do the following. All right, I'm gonna call this angle 1. This is angle 2. And this is angle 3, angle 4, angle 5, and angle 6. Okay? Everyone understand that? What I'm doing here? All right. So first of all, you are going to have the, so here's the proof. Okay. So first of all, you're going to have angle 1 is the same as angle 3 plus angle 4. Anyone remember what's the theorem? What's the name of theorem? What's the name of that theorem? The angle 1 is the sum of angle 2 plus angle 1 is the sum of angle 3 plus angle 4. Anyone remember the name? It's the exterior angle, right? Exterior angle theorem. Does it make sense? So you got the exterior angle. So angle 1 is the exterior angle of the triangle, right? The exterior angle of a triangle equal the sum of the other two remote interior angles, right? So that's called the exterior angle, uh, theorem, okay? And similarly, I can have angle 2 equals angle 5 plus angle 6, same reason, okay? So if I add them together, wait a second, let me do it. Let me wait a second. Let me first finish the first one here. And now I claim that angle 3 and angle 4 are the same. Okay, why angle 3 and angle 4, they have the same measure? Well, this is because you have the OP equals the OQ, right? They are all equal to the radians. So they all equal to the radians, right, of the circle. And so angle 3 equals angle 4. Why? Because they are isosceles triangle, right? It's the isosceles triangle theorem, right? Isosceles triangle theorem, right? So that's for this isosceles triangle theorem, right? And now, so from here, I can say that the angle 1 is twice of angle 3, because angle 1 is angle 3 plus angle 4, but 3 and 4 are the same. So angle 1 is twice of angle 3, right? It's a substitution, right? Substitution, sub, all right? And so similarly, I can do the same thing for angle 2 is twice of angle 5. I just work on the triangle of the other side, right? I can work on the triangle of the other side. So same thing. Maybe I can just add some details. Just do that. Just give you some details, right? So angle 2 is angle 5 plus angle 6, and angle 5 is the same as angle 6, and therefore I do substitution is 2 times of angle 5, right? And I want to add them together. So suppose this is my equation 1, this is my equation 2, 1 plus 2, I got angle 1 plus angle 2 equals 2 times angle 3 plus angle 5. And I'm done. Because what is angle 1 and 2? Angle 1 and 2 is just the angle of POR. And what is the angle of 2 and 5? Angle 3 and 5. Angle 3 plus angle 5 is just the angle of P, Q, and R. And then you divide both sides by 2 and you get the answer. Does it make sense? Right? So let me give everyone one more minute. So that's our first theorem in terms of the circle. All right, first theorem in terms of the circle. Everyone's okay? Well, very good. So you can say it's the end of the proof. That's finished. But actually, in geometry, where we have to sometimes we have to be very careful, because for this one here, people might say, why? So if you do this, okay, well, why OQ has to be inside PQR? So why so for this proof here, we are assuming that the OQ is inside the angle of the PQR. but sometimes it may not be in that way. Can you see that? So for this case, actually it's the first case, case one. We are assuming that the the OQ is inside the angle of PQR. But you might say, well, what happens if OQ is not inside that? So we still have to deal with the other case. Does it make sense? Right? So many people just thought it's the end of the proof. It's not the end of the proof. We have to take care of all of the possible cases in mathematics, especially in geometry. When you draw the graph, right? The position of the point is changed, then the answer, the conclusion may be changed sometimes. Right. For this case, it's not changed, as you can see later. Just give me one more minute. I'm going to show you. But I just say, in general, if the position of the points and the lines are changed, right? If the positions are changed, then the conclusion time you could change from a positive to a negative. That's normal, right? For many theorem, we will see that if you change that inside outside, right? You could change that from positive to negative. So I still take care of the other side. Okay, so let's see the other side. Second case. So let me move down. Okay, so let's see. All right, so the other case, let me draw the picture again. Oops. All right, so I have the P here, still here, and R is still here. But it is possible that your O is here, right? It is possible that your Q may be here, right? If your Q is here, and then you see that the positions of the O is changed, right? So let's take a note. Okay. So the picture will be this. It's a little bit different, but you can prove in a similar way. So let's see. I'm going to still do this. I still do that, right? So you still want to show that the same conclusion, right? The angle of PQR is half of the angle of the POR. Okay, so how can you do this? Where I can do in a similar way, but in the previous way here, I use angle 1 plus angle 2 to get my answer. But now I should, what should I do here? So basically, I should use this as my angle 1. So this is my angle 1 here, right? So this is my angle 1. So angle 1 means that, so that's the second case, right? So case 2. Okay, so angle 1 basically just means your angle of the P, O, something here. Let me O, P, Q, P, Q, let me use R here. Okay, R here is a P, Q, R, right? And your angle 2 is defined to be, that's your angle 2. So this is your angle 2 here, right? Angle 2 is oh, I have R already, so sorry. Let's see. Let me use a T for that. So that's a T, and that's a T here. So P, P, Q, or P, O, P, O, T, and then R, O, T. Right. Okay, everybody's okay? Not, and then the rest of them should be still fine. Okay. Let me just try to do that one by one. Okay. I'm going to call that, so that's angle 1 here, and the angle 1 is actually the sum as angle 3 and angle 4. So this guy is angle 3. Let me write 3 here. This guy is angle 4. Can you see that? So angle 1 is angle 3 plus angle 4. But again, angle 3 and angle 4 are the same because it's the same radians and it's an isosceles triangle. So I'm going to just quickly write that to be 2 times angle 3. So far, so good, right? Okay, now let's do the other one here. Angle 2, I'm going to write that into, I call this guy to be angle 5 and this guy to be angle 6. So angle 2 is actually angle 5 plus angle 6. Do you see that? Same theory, right? Exterior angle theorem, right? But angle 5 and angle 6 are the same because you get the isosceles triangle, right? You get isosceles triangle. So this is 2 times angle 5. Does it make sense? Okay, now I'm going to do the subtraction. That's what I say that. Usually, if the positions change, the part originally it's a sum. Now you are going to take the difference. Okay. So this is my first equation. This is my second equation. All right. So I'm going to have the first equation minus the second equation. I already have angle 1 minus angle 2 equals 2 times angle 3 minus angle 5. Okay. Well, what's the angle 1 minus angle 2? Well, that's exactly what I'm looking for, right? Angle 1 minus angle 2, that is the angle of, let's look at that. So this is the angle 1. I'm going to write 1 here. 1 minus 2, so that's the angle of the POR. Okay. The right hand side, what is angle 3 minus angle 5? 3 minus 5, again, subtract. So that is the P Q, and R. And on that. Does it make sense? Right? So you have to take care of the both cases, but hopefully they are just similar. No big deal, right? Not very complicated. So anyway, I'm gonna give you 1 minute. So for the first theorem for circles. Okay, first theorem for circles. Are there any questions? So from here, basically, we get immediately a coronary. The coronary will be in the previous picture, right? What's the previous picture? Where if you have a bunch of inscribed angles, as long as they are inscribed angles of the same arc, then they are always the same, right? Does it make sense? So if I have, so the coronary will be, let's see, the coronary, suppose this is the angle 1, where I don't use the 1, 2 again. Let me use alpha, beta, and alpha, beta, and gamma, right? Our angle alpha, angle beta, and angle alpha, beta, and gamma, they are all inscribed angles, but to the same arc, right? So as a coronary, that means angle alpha is the same as angle beta, is the same as angle gamma. So everything's okay as long as they are inscribed angle to the same arc. Then all of the inscribed angles are the same. So that's why we can call them. They are all inscribed angles of PR. Okay, does it make sense? Very good. So basically, that's what I want to talk for the circle. And then for the rest of the time, I'm going to go back to say a few more words, one more idea about how to estimate the pi, because again, that's from history of mathematics. I think this is very, very important in our history, right? How the human being, right? How human being can recognize the circle, right? I think this is very, very important. Okay. All right, so let's go back to estimate the pi again. Okay, second idea. Estimate the pi. Okay. Well, so the idea is actually quite simple. Again, it's very straightforward. So let's see. So suppose you get uh, basically suppose you have a circle, right? You have a circle here, and then I want to get the inscribed a regular polygon, right? And then I have a circumscribed regular polygon. So let's say, suppose for here you have a regular polygon, right? So this is a regular polygon. I just draw a one triangle. It's actually all of this, right? So that's a regular polygon. But this is inside. But then you also have an outside, right? So for the outside, basically you make it a little bit bigger, right? And you can cut that in this way. All right. So this is, let me call that O, and this is A here. Anyway, and then you can do lots of other stuff here, right? And so on and so forth, right? So you can do many other stuff here. But anyway, so let's say let me use AN for the perimeter, of circumscribed a regular polygon of inside regular. Let me just say regular angon, a polygon, but you have an inside, so it's just an angon. Many people just write that. Okay, and the Bn, I'm gonna use the perimeter of the circumference of the inscribed of the inscribed the regular angle, right? And because of that, and let's assume that it's a unit circle, all right? So assume that the R is equal to 1. So I'm going to have the circle, the perimeter of the circle, which is 2 pi R, right? So 2 pi R, and that's less than the AN and bigger than the BN. Right? Everyone understand that? So that's just the so this is the idea where you might say, oh, that's so easy. What? That's so easy. Certainly, that's true, right? It's a 2 pi is bigger than the circumference of the inscribed regular polygon, and it's smaller than the circumscribed regular polygon. Right. So far, so good. But the problem is that where if you just work for n equals if you just for n equals n equals 6, right? Why it's a 6? Because 6 is easy, right? If you look at the 6 here, 6 is just a regular hexagon, right, of the side 1. So I know that the inscribed regular polygon of side 6, I know the answer. That's easy, right? So if that's equal to 6, the bn b6 is just equal to 6, right? So this is b6 here. And how about a6? A6 is not too bad. You just take a look at that. So basically, the idea is that if I just go to here, right? If I just go here, I look at wait a second. So basically, I want to see the ratio here. So you see, let me draw this one here. This is okay. So how do you get the A6? Where A6 is the let's see how you can get this. Okay. Where basically you can see that. So if this is equal to 1, right? And this is a right triangle, This is 30 degree, and that's a 60 degree. So we have the spatial right triangle of 30 degree, 60 degree, and 90 degree, right? And so if this guy is 1, then how about this one here? This guy here is the, let's see, I know it's a what the regular ratio will be 1 to root of 3. But I treat the root of 3 side to be 1, so I need to go down by, it's actually the 1 over root of 3. Does it make sense? Right? Because originally it's a 1 to root of 3, but I treat the root of 3, reduce that to 1. So the side of 1 is become 1 divided by root of 3. But the other side is also 1 over root of 3. So it's actually equal to a 2 over root of 3 and times 6 here. So that is a A6, right? And if you work on that, it's actually 4 times root of 3. And so if you just work on that, 2 pi is smaller than 4 root of 3, bigger than 6. Pi is bigger than 3 and smaller than 2 root of 3, which is roughly, I need a number, something, 3.4 something. Okay, that's not very good. As you say, oh, that's too bad because it's if you give me an estimate of 3.4, that's not good. But the idea is the following. Okay, the idea is the following. Although for n equal to 6, it's not good. It's not very good. But I can keep on working. I can do n equals 12, right? So what happens if n equals 12? And if n is equal to 12, it's not very good. What happens if n is equal to 24, n is equal to 48, 96, and so on and so forth? And then in history, someone did that for, let's say, when n equals 1,536. All right. It's a long story, okay? But since we don't have time right now, to make the long story short, okay, if you just keep on working in this way, when n equal to 1,536, and you get the pi to be between, this is 3.1415926. The other one is 3.1415927. That's impressive. Okay, that's impressive. And the year, who did that? Or someone in his history. And I'm going to write down the name. And we should memorize this great person. Okay, so it was done by, okay, someone with the last name Zhu. Okay, it's a Chinese name, so I'm gonna write down here. Chong Zhi, and he is from for the year of 429 up to 500. So sometime around that year. So that's about 1,500 years ago. Okay, someone did that. But what's the idea of doing this? If you just say, well, how could I estimate the side of the regular polygon of 1,536 side? How do I do that? That's not easy. If you just do that out of blue, that's very, very hard. So the key idea is a formula. It's not just like you just estimate that one by one. It's not just like that. You have to have some key idea, the strategy. So what's the strategy? Okay, so let me quickly show you the strategy. Okay, here's the strategy. The strategy is that he managed to do the following. If you give me AN and BN, all right, if this is a given, I have some kind of way to estimate A of 2N and B of 2N. Basically, that's the idea. That kind of recursion is very, very important because otherwise, how could you do that for 1,500? That many sides. It's just impossible. You have to get a strategy. The strategy is to get such a recursion. And I'm going to show you I can prove, we don't have time. It's a little bit complicated, but you can still do it. We just don't have time to do it right now. So the idea is the following. I have 1 over an, oops, almost done. I just need a 1 minute to give you the recursion. So 2 over a of 2n, okay? And then b of 2n is equal to a of 2n times bn and take a square root. So that's a way to change from an bn to a of 2n and b of 2n. Can you see that? Right? So first of all, you can go from here to get the a of 2n. Does it make sense? And after you get that, and you go to the next line, and you can get the b of 2n, right? You can finish this. So you can just repeatedly do that. If you have, a very, very big scratching paper, right? You just work on that, just continue to work on that one by one, one by one, one by one. Eventually, if you have enough time, right? And then you can calculate the circumference of the regular polygon of 1,536 sides. And eventually you get such an amazing estimate. Okay. Well, we didn't go to all of any of the proof, because the proof, if you Google the internet, you can see the proof. It's not too bad. The proof is a little bit complicated, but I think at your neighbor right now, this is suitable for our neighbor. I just don't have enough time to go over the details, right? But you are welcome. You are certainly recommended to Google the internet and find the proof. The proof is not bad, not bad. It's just a one-page proof. Okay. Anyway, so I'm done for today. Are there any questions? Very good. So see you next time.
Thank you.
Bye.
Thank you.
Bye. Thank you.
Yeah.
Bye.
Bye, everyone.
Thank you. Bye.
Bye.